more. This is the base version, and I still, I didn't.
Yeah, you're still off a bit. Okay, so here's your problem. All right, this is a good comment for everybody working on problem set 2. Homework, the problem 1.1, 1.2 is a little bit of a tricky unit problem. So you end up having, so like in 1.1, you're going to have something that looks a little bit like the delta G of the reaction. By the way, we're going to talk about Gibbs free energy today. We'll get to that today. It's a function of pressure is equal to the change in the molar volume times the final pressure minus 1 bar. All right, so you should have an equation like this by the end of 1.1's derivation that looks like this. And the idea is to set this equal to 0. Right, that's where equilibrium is. We'll talk about that today. I know I'm jumping ahead a bit. Let's deal with units. Units are the tricky part here. You have kilojoules per mole on this side. Right, so we need to make sure that we have kilojoules per mole or joules per mole on both sides. It's easier for us to just put this in the joules per mole, all right? Because joules are the SI unit, all right? So let's just put everything in SI. What is a joule? A joule is a kilogram meter squared per second squared. Okay, so on the right-hand side, we need to choose units that are appropriate for these units on the left-hand side. All right, so what that means is that our volumes need to be in meters and our pressures need to have units of meters per second and kilograms, which is force. So the units that we need over here for volume, of course, the volume unit is easy, right? Because the only volume is cubic length, so that's meters cubed. So you need to convert your molar volumes into meters cubed per mole. And then you've got, this is originally in bars, right? But bars are not an SI unit, right? 1 bar is defined as a specific number of SI unit pressures. And the unit of SI unit of pressure is what's called the Pascal, or we notate it PA, all right? And here's the definition. 1 bar is 10 to the 5 pascals, and 1 atmosphere is 101,325 pascals, okay? Depending on what units you're using, these are useful comparisons. All right, remember 10 to the 5 is 100,000. So an atmosphere and a bar are very close together. All right, so let's...
Is 1 bar 10 to the 5 or 10 to the negative 5?
10 to the 5. Pascals are small. Right, and so let's just make sure the units work out here. So just some quick math. Quick unit math. A Pascal is defined, pressure is defined as force over surface area, which has units of newtons per meter squared, right? Force is newtons. Now, what the hell is a newton? Well, remember F is equal to ma, that's Newton's laws. And so the units are length, so meter, times the units of, or sorry, the unit of mass is kilogram. And the units of acceleration are meters per second squared. Okay, so the total units of pascals is newtons per meter squared. So that's kilogram per, let's see, meter, kilogram per meter per second squared. All right, so let's multiply now pressure by volume. I'm going to work right to left, like an Arabic mathematician. And so that's going to be, pressure is kilograms per meter second squared, and volume is meters cubed, which is kilogram meter squared per second squared, which is a joule. Okay, so 1 joule is equivalent to 1 Pascal meter cubed. All right. Right, so what you need to do, there's two options. One is you convert the right-hand side to pascals and meters cubed, or you can convert joules into units that are pressure times volume. I think it's easier just to convert the pressures, to convert 1 bar to 10 to the 5, delta V bar, the molar volumes in the meters cubed per mole, and then just multiply your G's by 1,000 to get joules, which you don't even need to do because you're setting it equal to 0. Should be fine. Is that helpful? Cool. So there's a special type of unit, a joule. So here's another one. Here's another conversion. Let me just do one more for you. This one's useful too. If you would rather use energy in terms of pressure times volume, 1 joule per mole is equal to 101.325 atmospheres times liters. So you can also use this conversion if you want to use liters and atmospheres as well. Let's post this on this too. So.
I think my problem was that I was trying to do it in bars and I should have been doing it in pascals.
Yes.
Okay.
This is a common problem people have with this. In fact, in the office hours, I went through this a couple of times. So just make sure your units are right on both sides. Okay. Let's move on. Spent a lot of time talking about enthalpy. I'm kind of done talking about enthalpy. Let's kind of take it to the maximal limit of what we understand. What have we learned? What can we finally learn from our enthalpy and heat capacity calculations? And then I want to pose a question about in particular about boiling and enthalpies. That will lead to this idea of that will eventually lead to the idea of Gibbs free energy. Okay, so hopefully by the end of this class, we have a concept of what free energy means and why we're going to use, and then initially for the rest of the semester, we're going to really focus in on delta G. Delta G is going to tell us everything you want to know about a system or a process. So again, I'd like to motivate this conversation a little bit. By let's just finish up a little bit about enthalpy. I wanted to make some notes. So from last class, it's actually the last 2 classes, but last class we kind of worked it out and did some problems. But we saw that the enthalpy of something at some temperature is equal to a standard enthalpy at standard conditions, right? Whatever we choose to be standard conditions, plus the integral from the standard temperature T naught to our final temperature T of the heat capacity, which is a function of temperature, dt. All right, this is something that comes up and I just want to, this is a really, some of you might think is a really dumb comment, but this is something that comes up and it's just a point of confusion. Sometimes when I write things like this, you should think of this as like f of x. Some people think of this as delta h times t. I've seen that in my homework before. That's if I ever write something that looks like this.
So that's also a function of
That's a function of t.
Okay.
It's f of x. So it's already someone's confused here. So if I were to write,
No, I figured that out.
if I wanted to write delta h times t, I would write delta h times t. Okay. So when I put parentheses like this around one variable, or if I have multiple variables of commas, I mean, it's a function of temperature. So what else can we learn from this? Of course, we saw that, right? And we saw that we can represent the heat capacity using the Shomate equation. And there are other types of equations we can use that says that the heat capacity can be written as just a function of T. All right, you guys will play around with these on the homework. Okay, so the heat capacity is just a function. I mean, there is a kind of, in some sense, a theoretical way we can actually compute the heat capacity for any molecule. that's not an issue for an entropy chem course. So the way we're going to look at the heat capacity is it's an empirical measurement that we can make using experiment that allows us to define our thermodynamic functions of enthalpy and entropy. All right. So in fact, there is a way, I think, if you give me a molecule, and you tell me its different motions, its vibration, its size, its structure, and things like that, I can write down and calculate in Excel, if I wanted to, the actual heat capacity of the material at a given temperature. Something that is, in some sense, as a formula, an algorithm allows you to calculate it. That's a little beyond this course. But the idea is that it gives you some function that changes with temperature, and the function generally kind of looks like a polynomial with maybe some 1 over t left. Okay. And this is an approximation. Okay, it's just a useful approximation because it's easy for us to integrate functions like this. You know, anyone who's taken calculus 1 can figure out how to do this. What else can we learn from this? All right, so we've got enthalpy, right? But there's another thermodynamic variable that we have dealt with, which is entropy. And the fact is that actually if we know the heat capacity, we can also calculate the entropy. It's a very, very simple derivation. So entropies can also be determined by the heat capacity. All right, let's see how that works. So what we need to do is to go back and think a little bit about the definition of enthalpy. The way we define enthalpy was equal to the total energy of the system plus PV. Remember, we took the energy and we subtract off the pressure volume work at constant pressure. We're just left with the heat change.
Wait, so now H is the entropy.
No, I haven't gotten there yet. We're starting here. I'm starting with this definition.
Okay, so but H is still entropy.
Yes, nothing's changed. So let me be more clear, right? This is our definition of enthalpy. Right, and we saw one of the things that, and we also know is that for a constant pressure system, that U is a function of the number of particles, the volume of the system, sorry, the pressure of the system, I apologize. The pressure of the system and the temperature of the system. Okay. And so du, this is what we derived before, is equal to this is just the Gibbs fundamental theorem or fundamental equation of thermodynamics, dN minus V dP plus S dt. Okay, and we're adding plus PV here, and we're going to assume that dN is 0, that the moles aren't changing. All right, we'll talk a little bit about this. This actually not this class, but when we get back, we're gonna not assume this anymore, and we'll see why we need to do that by the end of this class. That means that dH I'm sorry, let me replace this. I want to replace this at constant entropy, ds. So my apologies. I'm just going to flip the S into T plus TDS. And so what that means is that we can get rid, so dN is 0, so that term goes away. And we're adding our change in enthalpy, we're adding out, right, the energy due to work right here, VDP, we're getting rid of right here, right, by adding it back, right? So enthalpy is U plus PV, so any negative PV terms go away. So this goes away as well. And so we're left with at equilibrium that DH is equal to TDS. right? So now we have a direct relationship between enthalpy and entropy. And a system at thermal equilibrium, the entropy, the change in enthalpy is equal to the temperature of the system times the change in entropy. Right, so all we have to do now is then say that ds, the change in entropy, is 1 over the temperature times the change in enthalpy. Well, we have an equation for the macroscopic change in enthalpy. It's this right here. All right, so all we have to do to calculate entropy is we take the enthalpy and divide by T. So therefore, the entropy, the change in the entropy at some temperature of our system is equal to a standard entropy plus the integral from our standard temperature to a new temperature of the heat capacity divided by temperature dt. Right? So in order to calculate the entropy, all we have to do is take the heat capacity function we have here and divide it by T and then integrate. I mean, how easy it can be, right? Also now what that means then, right, that Cp of T divided by T is going to be, using the Show-Mate equation, A over T plus B plus Ct plus dt squared plus E over T cubed, right? So by having the heat capacity, we can determine the entropy at any point, and we can also determine the enthalpy at any by dividing by T. That's so convenient, right? So if we can measure heat capacity, we're done. Heat capacity tells us everything we need to know. So that's going to be really nice. Eventually, we're going to start thinking about delta G. And when we get to equilibrium, everything about equilibrium is determined by the value of Gibbs free energy, or the enthalpy and the entropy of the process. And so if we can measure the heat capacity of everything in our material, we can calculate for any temperature, any pressure, anything we want, the change in entropy, the free energy. And if we know the free energy, know the enthalpy and the entropy of a system, we can calculate the equilibrium constant, we can calculate, yields, how much products, how many reactions you have, what it equilibrates, right? All the chemical information about a process can be determined from these two numbers. And they're all related to one thing, the heat capacity. Yes, ma'am. Oh, okay, great question. Sorry, this is just math notation. Dot, Greek triangle dot means therefore in mathematics. It means therefore. Sorry, that's a shorthand that I use a lot. It means, I think it technically means thus, but we'll call it therefore. Anytime you say that, that just means I'm just talking. Rather than just not write it. Okay. All right, so we'll come back to these equations when we build up a little more tools where we need to use enthalpy and entropy. One thing that we haven't determined yet. We've determined in some sense how to define a standard enthalpy, right? We use these primitive materials, right? These common chemical elements and compounds that we basically set to be zero at room temperature and room pressure. Totally nothing wrong with that. The question is, do we also do that for entropy? How do we determine this value? It's a good question. And so what I want to do is just tell you the answer to this question. It's much easier than enthalpy. For entropy, it turns out we don't need to define some relative set of, or some sort of reference set of materials that we use as a relative gauge of energy. Said entropy, by definition, has an absolute value that we can reference against. There is, in some sense, zero entropy. You guys have calculated zero entropy. In problem set 1, when you looked at the box that you cut in half and you pull the partition in the middle, allow it to mix, the entropy of that initial box, where you pull the divider, was 0. Here's a state or a definition of a system and a process where the initial conditions has S naught to be 0. That turns out to be something that is true always. So I'm going to there's not a derivation, it's rather a statement of a law. And we've been giving you lots of different principles and laws over the last couple of months. This is our last one in some sense, the kind of final equation of thermodynamics that we need, or our principle. And it's called the Nernst postulate. Sorry, my laptop is lagging just a bit. I have a feeling it's going to crash. I wish it would just crash outright instead of just hanging like this. Okay. All right. Well, let me just restart it. Just a sec. No, we wouldn't have this problem if they just built blackboards in these rooms. Okay, so I lost my notes that I just had. Let's see if I can pull them up. Oh, I bet you they're right here. Oh, very good. All right, we haven't lost any place. Fantastic. Okay. Right. So this last kind of statement of fact, we would call a postulate, which is just something we assume to be true. And there are many, many experiments to prove that this is true. It's called the Nernst. Is it going to crash again? Okay. Try one more time. My wife is judging me. Okay. Right. The Nernst postulate. Right. If you were to pull up a textbook, a traditional chemistry textbook, this is generally what's called the third law of thermodynamics. Right. I have not used the term laws in this class because I take a slightly different approach than most people do. Right. But this is what's called the Nernst postulate, and it's a very simple statement. It says for
Oh, no. Not again.
I got one word in. I got like a couple words in. I don't understand. Usually this happens when my laptop is hot, but it is not hot today. It's not that either. If that were the case, my share screen would fail on a regular basis. All right, let's try one more time. If this doesn't work, I'm just gonna let you guys go home. There's no one. I don't have any markers, and I don't want to write everything on the board. Unless someone has markers and want me to write, then I will.
I have markers.
All right, we'll try one more time.
Yeah.
So like, this is like able to be part of the recording when it's.
Yeah, I'm gonna have to cut it out. Nernst. Let me erase that. Of course, now I can't even spell. Third law. Okay. All right. Very simple. For a perfect crystal, right? The entropy of a crystal goes to 0 as T goes to 0. Otherwise, which means pure materials that aren't perfect, we'll have to define what that is, S approaches a constant value as T goes to 0. So this is why we do not need a relative reference for entropy. Because what we're guaranteed is that no matter what material we have, as long as we can cool it down low enough, we can find the absolute value of the entropy. If the material is a perfect crystal, I don't really know what that is yet. That entropy goes to 0. And so we know that by extrapolation, that no matter whatever material we have or whatever, that entropy is always referenced to itself, to its 0 value. Right. And that value, again, comes from the fact that in a molecule, its ability to store energy through heat capacity is a function of the molecule itself. It's not a product of anything else. So when you take all the heat out of the system, there is, in some sense, no more energy for the molecules to use. There is no heat. So by definition, there is no entropy. Therefore, the entropy should go to 0 as T goes to 0. And enthalpy doesn't have that property because, again, enthalpy is a function of total energy. And total energy can be negative and positive. You can have negative potential energy, which we call attraction, right? You can have negative potential, you can have positive potential, you can have kinetic energy, and so on. Enthalpy is a range that varies from plus infinity to minus infinity, right? Because there's not really a place you can put a 0 point there. There's no, since the bounds are infinite on both ways, there is no real 0. But entropy is always positive, right? That was one of the things that we determined at the beginning of the class when we talked about it. It's a positive thing, and it always increases as the temperature increases. So therefore, it always has to hit a minimum. There is no negative value for it. So there's an absolute reference. So the idea is that a perfect crystal, if we were to plot the entropy as a function of temperature, a perfect crystal would look something like this. As it goes to 0, it goes to some limit. And for a regular material, the entropy would approach some finite value like this. And this is what we would call S naught, the standard entropy. Okay, the way that, right, so that would be our absolute entropy. Now, the way that chemists typically reference entropy is at 298 and 1 bar, right? To keep things consistent, chemists define the entropy at 298.15 and 1 bar, just like we do for enthalpy, right? So that we can compare them apples to apples in some sense, right? So this is the absolute reference, if you will, right? That's the absolute reference of entropy is at 0 Kelvin, but we choose in lab or in chemistry to pick the value right here at 298.5. That's our relative reference. So we always report our entropies at that point, but they're all referenced relative to this.
Wait, what's the site?
Absolute.
Absolute.
Absolute. As in, yes, it's the absolute reference. So, of course, you may ask, what the hell is a perfect crystal? And in fact, there's not really a real perfect crystal. Let me show you some examples. I think a good example is carbon. So if we look at carbon graphite, the value is 5.7 joules per mole Kelvin. For diamond, which is a crystal, the entropy is 2.4 joules per mole Kelvin. So it's not exactly zero. Right? So it's not exactly zero, but you take a diamond, you take it all the way down to the lowest possible temperature, and its entropy is 2.4 Kelvin. It's just the absolute limit. Now, why these values? Why is graphite higher? All right, well, let's go back to problem set 1. So from homework 1, we had a really nice equation that we used to calculate entropy. Right? KB log of W. Remember, W is the number of configurations of the system. Right? And we're in moles, so let's just do R ln W. Right? So we can estimate from these values, what does W look like for graphite and diamond? How many unique configurations of graphite are there in graphite, and how many are there for diamond? And of course, there's less for diamond, right? Because there's only 2.4 joules, right? So there's clearly less configurational entropy in diamond. There's less ways for the atoms to rearrange themselves in diamond, and there are more for graphite. Right, so let's look at those two numbers. What is W for these instances? Right, so the W for graphite is going to be S over R, or sorry, the log of W. It's S over R, which is 5.7 divided by 8.314. Which is 0.6686. And that means that W is going to be e to that value. Sorry, I've typed in the wrong. W is approximately 2. Right, so graphite has 2 configurations.
I'm a little confused on something, Brenham.
Go ahead.
The carbon, it says carbon, and then what's the CR?
Crystal.
Crystal, okay.
Crystal. This is solid, and this is crystal and right. Right, because as you guys know, graphite is not a crystal. Graphite is a soot. It's just a solid. It's often a powder. Whereas diamond, as you guys know very well, is a crystal. Distinctly a crystal. What does that mean that it has 2 configurations? In some sense that there's only 2 ways to take graphite material and arrange it. All right, let's go look at the structure of graphite and maybe see if we can understand what that number means. All right, so again, we'll go look at Wikipedia. I think there's a structure of this, right? Here's a nice picture of the way that graphite is stacked. Graphite is just huge benzene rings, right? No hydrogens, all the hydrogens stripped off, and you just have this, what we call tessellation, like a pattern of a flat pattern of benzene rings. What we call this is called a graphene sheet, and graphite are stacks of graphene sheets. pressed on top of each other, stabilized through van der Waals interactions. Okay. There's so graphite is a multi-layer material stabilized by non-covalent interaction in the layers. So what would constitute two different ways to determine this, to set up the structure? Well, here, let me show you. It's a bit like thinking about honeycombs and how honeycombs arrange themselves. I'll do my best to draw this. So imagine I have one sheet that I draw in white here. Not the best drawing, sorry, let me fix that. All right, there's one sheet. And then on top of the sheet, the next sheet on top of it, I just take the same sheet in the same arrangement and shift it a little bit. Translate it, right? So I have the sheet on top of it, and it's parallel to the sheet below it. All right, so we have two parallel sheets. All right, so this is configuration number one. But the other thing I can do is rotate it 90 degrees and have them perpendicular, right? Where, for instance, two parallel bonds that are identical, right? This one and this one, instead of being parallel, are now perpendicular to each other. So let me see if I can draw that. So I'm going to draw the second sheet precisely the way that I drew the first time. And this time I drew it much better. Right, and the second sheet is going to have a configuration that looks like this instead. Oh, I need a straight line here. Like this, where they're perpendicular instead. I'll draw it like this. So we have, this is parallel to this, and this is now just parallel to itself, and this is perpendicular. All right, so we have perpendicular sheets now, where the other sheet comes in at 90 degrees relative to that one. So any place where two edges would align, now you have an edge in a, sorry, here you have vertices aligned, vertices are aligned, and here you have a vertex aligned with an edge. All right, so it's off by 90 degrees. So here's your two possible configurations of graphene. These are both equally possible because at the bulk limit, there's really no difference in terms of the interaction energy. They're both basically equally likely. And so therefore the entropy is exactly log of 2 times R, because there's two different ways to do it. And this is what I mean by a perfect crystal. Graphite would be a perfect crystal if there was only one configuration, right? If there was one configuration, W would be 1, log of 1 is 0. Entropy would be 0. So a perfect crystal is a crystal that has only one possible arrangement of its atoms. Right? So let's go back and let's look at diamond, right? Diamond's a little funky. Diamond's some number between 0 and so basically between 1 and 2. Right, so diamond actually has a ratio. Let's calculate what that ratio is. So that's the e to the 8.314 divided by 2.4. or sorry, 2.4 divided by 8.3. 1.33. So this is 4/3. Kind of a strange number. But what this is let me see if I remember. It's one config of weight 1 and 2 configs of weight 2. Right? So there's one configuration that has a probability of 1/3. And there's 2 configurations that each have a probability of 66%. I don't quite have the math right. So it's a little more complicated, right? So there's some entropies can be kind of random values, but largely they're associated, right? W is associated with some statistical weight of different arrangements, and diamond has a small but kind of somewhat complex way to arrange all the atoms together. So that's where these numbers come from. So diamond never has a 0 entropy because it always has this configurational uncertainty to it. Different ways to arrange the atoms in a matrix. And how to basically align the different cells of how all the cells of the diamond align themselves. So there's nothing you can do about it, but the point is that you can be anywhere in the universe, any instrument, as long as you can cool it down, you get the same value for diamond for its entropy, no matter where you are. It's an absolute value. Right? So that's different than enthalpy, right? Enthalpy is a relative sense. There's lots of really, really cool examples of this. There's a really, really nice discussion about water's entropy. Water's entropy, in fact, was higher than you would expect. Liquid water is higher than you would expect from this argument. Sorry, ice. Water ice. Water ice actually has a higher entropy than you would expect from a crystal. In fact, it has more entropy than graphite does. And the reason why is for the same reason as diamond. There turns out to be different ways to arrange 6 water molecules in a crystal. There's ends up being 4 or 5 different ways to do it, and therefore water ice has a slightly higher entropy, which is one of the reasons why it's significantly less dense than crystals of its other types. As you guys know, water crystals tend to be kind of broad. They tend to be wide. They're wider. They're less dense than their liquid counterparts, and part of that is the fact that the crystal has amplified entropy compared to other crystals of the same kind, because it has that kind of configurational uncertainty, that there's different ways to arrange the waters that are equivalent, raising its entropy and therefore its standard heat. And what this means is that no matter what, no matter what you do, this energy is always contained inside the crystal. In some sense, I can strip away all the possible heat that I can do, but no matter what I do, I'm always going to have 2.4 joules per mole per Kelvin. That is in some sense built into the definition of diamond. The energy is always stored in there, even at 0 Kelvin. So what does that say about 0 Kelvin? It means that 0 Kelvin is impossible to reach, because the definition of 0 Kelvin is the absence of heat. And there are real materials always have heat in them. So it's impossible to pull them to 0 Kelvin. It turns out it's a little stronger than that. Even if your material has 0 entropy at 0 Kelvin, it still is impossible to reach 0 Kelvin. Because inevitably the material that absorbs that heat out of that material has its own entropy. And that heat will exchange back, and you can never lose that heat. Basically, the heat extractor causes the material itself to stay above 0 Kelvin. Because it's impossible, because then you'd have to remove the heat from your heat exchanger, and then you'd have to remove the heat from that exchanger, and then you'd go on for infinity. So it's impossible to ever reach 0 Kelvin for this reason. Okay, that's enough right now about numbers. 30-minute break. Let's put this together. So what I want to do now is pose a question to you. Let me move this over. Right, imagine that we have a container of water. Right, that we set to 298 Kelvin. And we're going to heat it just like before. This is open pressure. We're going to put water in here. Right, and I'm going to heat it. Let's just say initially the temperature, let me do this better color. Let's say the temperature is initially 298.15 Kelvin. Okay. Right, and I know I want to boil this water. Okay, so I go and look up the enthalpy of vaporization, right? How much heat do I have to put into this water at 298 Kelvin to boil it? Right, that's something we've been thinking about. Doing that on the homework. Right, I want to boil. So you go into your NIST and say, okay, let's look up the enthalpy of vaporization. At 298. And I forget the exact value. Say it's about 43 kilojoules per mole. I think it's about 43. So what do? Okay, I say, okay, I need, let's say I've got a mole of water in there. Right, so I got 1 mole of water, and I want to set my, right, I want to boil it. So how much energy do I need to put into my water? Well, if I got a mole, I just need to put in 43 kilojoules per mole, right? So I set my heater, right? So we're going to say naively, that's going to tell you that this is wrong. It's a little bit of a spoiler. We would say
It's 40.7. Sorry.
at 373.
Oh, at 370.
Yes, this is at 298. Yeah.
Oh, yeah.
But regardless but we'll come back to that. So hold on to that number for a second. We'll come back to that. We would say that the heater needs to supply 43 kilojoules per mole to boil the water. Right? Okay, so we go turn our heater and do that. What happens to the water when we turn that on? Does it start boiling immediately? No. What happens to it instead? It just heats. Right? So the water does not boil. It just heats. Heats up. And it begins to boil when? When does it begin to boil? 1 atmosphere. What's the boiling point of water?
373.
Yeah, 373. So it boils at 100 C. All right. And at 100 C, just like Angie just said, the enthalpy of vaporization is 40 kilojoules per mole roughly. Right? So the enthalpy really hasn't changed that much. But somehow I've gone from a situation where it's 43 kilojoules per mole, I put enough energy into it, it doesn't boil, it just heats up. And of course it starts to build a little more vapor. We keep feeding it energy, and in fact the requirements for the energy get less as the temperature increases. But we don't see any boiling until we hit that temperature anyway. So what gives? Right? We just said that enthalpy is something, right? Enthalpy is the heat required for a process to happen, right? That this requires 40 or 43 kilojoules per mole of energy to go. So why doesn't it go when we apply the required amount of heat. We're missing something. We're missing something. Like there's something special about that 373 point where now the water will actually begin to boil without any us even trying, right? It'll just start boiling. So what gives? I'm going to put that down here. It's a very scientific question. What gives? So let's answer that question today. And this introduces our idea of free energy. Gibbs free energy will give us an answer to this question. Why it doesn't boil even though we put in enough heat. But then when we bring it to the right temperature, it boils spontaneously. So let's talk about that idea of spontaneity. Right, that at this point at 373.15 Kelvin, the water just starts boiling spontaneously without any further input from you. To describe spontaneity, I think it's easier for us to do things in a constant volume process because then we don't have to worry about work. Right? I think it's easier to see this process in constant volume. Right? I'm not going to draw my usual box. All right, you guys know what a constant volume is. It's a pressure cooker. Here's a cork. dV is equal to 0. Water heater or water boiler. Okay. So that means that at constant volume, that means that T and P are the dependent variables. Right. So therefore, du is going to be equal to TdS minus PdV. And because it's constant volume, this goes to 0, right? Because we're at constant volume. CV process. Right? All heat. Right? So if that's 0, well, we can therefore say, therefore, there's the therefore sign again. We can say that du in this system is approximately equal to the change in enthalpy of the system. Right? And so in order for this process to go to completion, we need to have the energy change enough to satisfy the change in entropy. Remember, the entropy always increases, right? ds always has to be positive. Right? That was one of the first things that we defined in the first or second day of class. That entropy is an increasing, something that always increases. Always got to be positive. If any process is going to move on its own, ds has to increase. Right? That's why hot air escapes from a hot room into a cold space instead of cold air rushing in. Actually, the hot air escaping, because that's actually what prefers, the entropy prefers the hot air to escape. And so by this definition, we could say that this process, this is only satisfied when dH, which is similar to du, is less than or equal to TdS. And so what we need in order for this process for boiling to occur spontaneously, we need to always be in a situation where the energy that's being supplied to the system is enough to satisfy the entropic cost of the process. So our process has some change in entropy, and the process is not going to be spontaneous and occur until the amount of heat that we can put in is on the order of the change in entropy. So what this means is that a process is spontaneous. I'm gonna write this on the next spot. Meaning that it occurs without further input. When dH minus TdS is less than or equal to 0. Okay. So let's think about this in terms of water. So this might not, it's not easy necessarily to visualize what this means until we start thinking about it with a little bit of numbers and some intuition. So let's go back to our boiling. All right, so we know that delta H here is positive, right? And it's 40 kilojoules per mole, roughly. At 40, what did I say, 43. We'll do it at room temperature. Now, here's a question I'm going to ask you guys, and let's see if we can just intuit the answer to this question without calculating it. Is the change in entropy going from liquid to gas positive or negative? Does the entropy increase when you go to a gas or decrease when you go to a gas? Increase, right? Right, exactly. It's just less organized, right? More chaotic. That's all you have to think about, right? Think about ordering. Solids are the most ordered. Liquids are slightly less ordered, and gases are completely disordered. So entropy tracks that way. So entropy is also positive. Okay. So, right, when entropy is positive, that gives a driving force to the process, right? Because a process wants the entropy to increase. So this provides this increase of entropy to provide some driving force. What the entropy is, right? You kind of think of this as the energy that's the potential energy that's stored in the liquid that can be released as entropy to increase the entropy of the system, right? It's a driving force. It's some ability for the system to use its own energy for a process. All right, so, but the problem is that delta H is greater than 0, right? Which means it's endothermic, meaning for this process to occur, you have to input some heat. So we have an energy cost, right? So this is an energy cost for this process, right? It's endothermic. Heat has to come in. Okay, so let's say, for instance, that the heat that we bring into the system isn't enough. Right, so in this case, we have 40 kilojoules per mole, right? That's the required heat for the system. Right, and the system needs to have enough heat in the system, enthalpy, in order to facilitate the change in the entropy. Or maybe it's another way to think about it, is that we're paying, imagine that the vaporization is a process that requires you to pay Mother Nature. Mother Nature says, hey, I'll make your liquid a gas if you pay me my little racketeering, for protection. And Mother Nature says, I need this much energy, and the amount of energy that Mother Nature taxes you to convert liquid to gas is TDS. Mother Nature says this is how much energy you need. And if you don't bring in enough energy, have that flipped. I'm sorry. Right, have that flipped. Okay, so DH in this case is what Mother Nature says, hey, this is how much energy I need for this process to occur. And TDS is the amount of energy or the amount of money you have in your bank account, thermal energy you have in the bank account to spend. So if the cost is greater than the amount of energy that you have available, then the process is never going to be spontaneous. You don't have enough money to go. Okay, so when DH minus TDS is positive, the cost is greater than the benefit in this case, and therefore DH minus TDS is positive and it's not spontaneous. Well, this is the cost. And this is the available balance of energy in the system. And so if this is less than 0, that means we don't have enough money. Too broke to boil. Well, let me say less than 0. If it's greater than 0, or sorry, if it's greater than 0, we're too broke to boil. I apologize. Right? If DH is greater than TDS, we're too broke to boil. If we're less than 0, that means we have enough money. Right? And Mother Nature allows you to boil. And then there's the choice where it's equal to 0, where we have exactly enough heat in our system to boil. All right, that's an interesting point. Right? So we could certainly be rich enough to boil, but we can also be, right, we're right in between rich enough, and we have some money left over here, and we don't have enough money or energy. And here we're in the middle where we have exactly the right amount of energy. So what does that mean? Well, what that means is that in some sense, it's equally likely for you to go forward as it is backwards, right? Mother Nature says, well, yeah, you can go ahead. You've got enough money. But if you imagine you're rolling the dice, all right, and TDS varies a little bit, right? The system is fluctuating, right? And every time Mother Nature comes in, hey, do you have enough to boil? Sometimes it's less than 0. And you have to say, yeah, I can boil, and it boils. And then Mother Nature comes back and says, hey, do you have enough energy, enough entropy today to boil? And the system is fluctuated so that it's a little cooler than you expect, and you're too broke to boil. Okay? So you have these fluctuations that bring you above 0 and below 0. All right, so assume that fluctuates like this, up and down, up and down. All right, so every time Mother Nature comes in and checks your cash, 50% of the time you're too broke, and 50% of the time you're good to go. And so in the end, you average out, and it's just nothing, right? Equally likely for you to go backwards as it is forwards, to boil or to not boil. So the term that we have for this is what's called equilibrium. Both are equally likely. So both liquid and gas are okay. The system is just as equally likely to condense as it is to boil when you have exactly the right amount of energy. So we call that equilibrium in the sense of chemical equilibrium, right? Where it says that it's equally likely for you to have liquid or gas. In fact, what we'll find next week is that when we're at this point, and the system is allowed to equilibrate at delta G equals 0, meaning we set the temperature just right to balance this all out, that we'll find that our system our flask is 50% gas and 50% liquid. Equally likely, you've got half and half. So if we have 1 mole to start with at that delta G, you'll be 50% gas and 50% liquid. Equally likely to be at both. Right, so what I really should say is in some sense that there are arrows going both ways. Imagine if I have, let's think about it like this. This is another way. Imagine that my system has gas, and I'm going to go backwards to condensation. If I have a gaseous sample and vaporization has a positive value for this thing that we just calculated, vaporization is the opposite. So if it's greater than 0 for boiling, then it's less than 0 for liquefaction. So even though here you're too broke to boil, you ain't broke enough to condense, right? You've got tons of money to condense. Mother Nature says, please condense for me. And then on the other end, rich enough to boil, that means you're broke. The gas is too broke to liquefy. The entropy is going the wrong direction. And so when you're in this situation, you only have gas and it never liquefies. So the signs change when you reverse the order, right? And you go from G to L for condensation, everything disordered. So when it's equal, what does that mean? When delta zero is equal to 0, you have just as much money to liquefy as you do to boil. You have delta G equals 0 for both of them. So they're equally likely. Right? So it's a reversible process. Reversible and at equilibrium. Okay. So let's give this a name, right? This seems like a useful thing to have. You guys probably already can tell what this is. We're going to define what's called the Gibbs free energy. We call G, which is defined for a constant pressure system. As following. Right? That G is equal to, or defined to be, the enthalpy minus the temperature of the system times the entropy. Right. Just some notes for you. Typically, we write this in kilojoules per mole, reported in kilojoules per mole. And as you know, this is typically reported in kilojoules per mole. Entropies are much smaller. So typically, these are reported in joules per mole Kelvin. Right. So just make a note of that, that sometimes there's a unit disagreement between things in these. All right, and let me just put together what I just wrote. Right. So now what we can do, yeah, go ahead.
Together?
No. I'm just saying these are how they're typically reported.
Oh,
These are typical reporting units.
that's BS.
Like as in bullshit.
Yeah.
Can I tell you why?
Yeah.
So you guys might wonder why we change units a lot in chemistry. And in fact, when we go into next semester, there's going to be like 4 or 5 different energy units that we use. Well, there's a good reason for it. The reason why is because, again, there's lots of different ways to express energy. In this class, we talk about thermal energy, right? Which is joules, right? The reason why we use joules for S and not kilojoules is because typically the entropies of materials in standard conditions are less than a kilojoule. And scientists don't like to write things. They prefer to have units where kind of in some sense the standard value is unity in the unit. So things that are on the order of 1 kilojoule per mole or 110 kilojoules per mole are written in kilojoules. Things that are on the order of 100 joules are written in joules, right? Not kilojoules. So we don't have to write 0.001. The thing that people are trying to avoid is writing decimals.
But we already have scientific notation, so why don't they just use that?
Yeah, well, I know. So I know. So this is, and the reason why we have a lot of energy units in the other class and next semester is because we're going to do spectroscopy. And there we're going to correlate light, the frequency and the wavelength of light to energy. And so we'll have a new energy scale, which is the energy scale of light. And there we have energy units for the different types of light that we use in chemistry. So we use a different unit for energy when we're working in the visible than we do in the infrared, than we do in the microwave, than we do at NMR, which is in the radio. So we have different scales of energy, and in fact, with light, it's orders of magnitude different scales. Light, the amount of energy difference that we have in our electromagnetic spectrum is 10 to 20 orders of magnitude. So it's not really useful to use one unit for that big of a scale. So we use different units that are convenient for the application. My recommendation is to do everything in joules. All right, so let me just finish up my little spiel here for the last couple of minutes. So what we can do now is define a spontaneous process. Is one that occurs with no external and additional input of energy or force all right, and we use at constant volume the value of G determines the spontaneity. And so G, and we'll study this a little more next class, is a function of a constant temperature system, which is constant pressure system, NPT. Has three conditions that we just talked about. I'll just repeat them. If G is greater than 0, it's a non-spontaneous process, meaning it does not occur automatically at the conditions. At NPT. G can be less than 0, which means it's spontaneous. And if G equals 0, we say this is at equilibrium. Which means that the forward process is equally likely as reverse. Sorry, I'm running out of space there. Equally likely as reverse. Okay. You guys in chemistry we have different words for spontaneous and not spontaneous. In chemistry, we're doing chemical reactions, as we'll see when we get to equilibrium, especially. Delta G greater than 0 means reactant favored. Means that in a chemical reaction that at equilibrium, it prefers to be predominantly reactants, not products. And when delta G is less than 0, we call this product favored. Okay. Well, I ran out of time, but let me just go back to our water boil, right? So why is it that the water doesn't boil at temperatures below at room pressure? Why does water not boil at any temperature except 373? Well, it's because that delta G of boiling at temperatures below 373 is positive. Right? So it's not spontaneous. But not only that, what is spontaneous at those temperatures is the heat, is heating the liquid. So in some sense, when you apply that heat to the you apply 40 kilojoules per mole of energy to the liquid at room temperature, the liquid in some sense has a choice. It can use that energy to heat up to a higher temperature, or it can use it to boil. And Mother Nature says, okay, what's delta G for each of these processes at 298? And what you find out is that heating the material at 298.15 is delta G less than 0. And then above boiling, and the delta G is less than 0 for heating, and delta G is greater than 0 for boiling. And then when you hit 373.15, boiling and heating are the same energy. They have the same delta G, 0. And so any temperature higher than that, right? Once you drive over that point, delta G becomes negative at 373.15. And therefore boiling then becomes the spontaneous process and not heating. Which is why when water starts boiling, it stops heating. If both of them were negative delta G, you would boil and heat the water at the same time. But that's not what happens. What happens is that the delta G signs flip at the boiling point. And now boiling is spontaneous and heating is not spontaneous anymore. And chemistry, physical processes are lazy as possible. They take the easiest route always. And so once delta G flips and boiling becomes delta G less than 0, it only boils. And then it doesn't start heating again until you stop boiling, which is when you run out of liquid. Okay? So delta G tells us everything. If we can figure out the value of G at a given position, given temperature, pressure, number of moles, whatever, I can tell exactly what's going to happen to the system. Now, the one thing is that we're going to see as my last comment. So it says nothing about time. We might calculate that delta G for a process is negative. For instance, combustion. Combustion has a negative delta G at room temperature and atmospheric pressure. If that were the case, then cars would be completely and utterly useless because your gas would spontaneously combust the moment it left a pressurized environment, right? The moment you start squirting the fuel pump, just flames would come out. Obviously, that doesn't happen. The only way that happens is with a spark. So even though there are processes that have negative delta G, that doesn't mean that they're going to happen. What it does mean is that they will happen eventually, but there's no sense of when they will happen. So when it comes to combustion, for instance, delta G is less than 0 at room temperature, but the rate at which combustion happens at room temperature is astronomically slow. The idea is if you have a mole of octane and you put it in a container with oxygen and just let it sit there, it's going to take the entire lifetime of the universe for it to combust. It will combust after an infinity of time, but not in any reasonable amount of time, right? So delta G tells you something about the direction, but doesn't tell you about the speed or the rate. That's what kinetics is for. So I just want to distinguish those two facts. So what we're going to be doing for the rest of the class is focusing on these two aspects. Focusing on direction of delta G and what does it tell us about processes and how molecules flow, say, from products to reactants, reactants to products. And then what we'll do is we'll do kinetics, which is to quantify the time at which a spontaneous process happens. Okay. That's where we're at. You guys have a lovely break. We'll come back to Gibbs free energy just and close out phase transitions next week, and then we'll move on to equilibrium and kinetics. All right, have a good one, guys. Sorry I ran late. Thanks, have a nice break.